Michele Fornaciari, my tutor is Andrea Prati, and my tutor is Professor Rita Cucchiara. I talk to you about visual recognition of events, shapes, and places. The common thing about my talk is recognition. Recognition is the ability of a system to be aware of the monitored environment. In the field of computer vision, the system is fed with visual information, typically through a camera. I talk to you about these different tasks, recognition of events, shapes, and places. And my talk is divided in 3 parts, one for each. Now I go into the details of events. The events we are looking for are intruders in wide open areas. Wide open areas have this challenge between localization and identification task, because identification requires a zoomed view to see, for example, a person's face, while localization needs an unzoomed view to cover more area. To accomplish this task, we can use a different kind of sensors. With cameras, we can have camera is pretty good for localization, while RFIDs is pretty good for identification. But we need a sensor fusion system to merge this data. We also have noise, missing data, and complex scenarios, so we need a tool to manage the uncertainty of this data. We found that a good tool to manage heterogeneous data and uncertainty is the transferable belief model. This model is based on the belief function theory, and it's a model that represents the quantified beliefs held by a belief holder. It models the knowledge of the belief holder as a belief function. New information can be modeled as evidences, and when the knowledge is updated through combination rules, and when it's time to take decision, the Pygnistic transformation allows to take decisions. So this is an overview of the system. The video analysis module takes the data from the cameras and provides the tracking information, this identifier of the person and his position. The RFID analysis system takes the data from the RFIDs and provides its identifier and its signal strength. These data are fused in the idential fuse architecture that is able to say if a person is an intruder or is authorized to be in the area. The information coming from the sensors is used to update the knowledge of the system through combination rules. And when it's time to take decision, the Pygnistic rule is able to say if the person is authorized or not. We performed several experiments, mainly synthetic, with a different number of authorized people, intruders and tags. We can see a popular scenario in the faculty. We divided this wide area in different areas, and I show you the results for a simple case where there are 2 persons, A and B, and 1 intruder. From the graphs below, we can see that the system is pretty sure that one person is the person named A, the other person is the person named B, and the 3rd person is in fact an intruder. We can see that we use the TBM to fuse data from camera and RFIDs. This is the first time we saw it. And we use TBM to represent a variable hypothesis set. That is when a new person comes into the area, we can enlarge the hypothesis set. We provide a new formulation to generate evidences from data from RFIDs and cameras. The system has been effectively used to recognize authorized people and intruders in the stop environment, and the formulation through the TBM is very easy to extend. Some drawbacks are that the system is really difficult to work in real scenarios because of the very low quality of RFIDs, and since it's not the purpose of my PhD to investigate the quality of RFIDs, we published just the theoretical foundation that is pretty solid. Now I talk you about another kind of recognition. It is specifically of ellipse detection. This is a pretty popular topic in pattern recognition. We want to do this obtaining real time and good accuracy. We started with this topic because we wanted to segment a bike, and so we decided to go to search first for its wheels. But we saw that ellipse detection is a pretty spread topic, and there are a lot of applications that can use it, so we decided to go to the whole ellipse detection in general, not specific to wheels. So we want our system to detect in real time and with good accuracy. This is pretty new because we can see that state-of-the-art run in about, this is in logarithmic scale, we can see that state-of-the-art run in about 1 second, while our system run in 1 millisecond, in 10 milliseconds. So state-of-the-art algorithms are pretty slow. Even the one that is the faster, we can see that has not a good detection accuracy. So this is just the results. I skipped this. We see that our system is both faster and more accurate than state-of-the-art results. So, well, this is just the equation of an ellipse. We have to estimate 5 parameters. And now I show you the algorithm overview to show you how we tackle every step. Well, we first detect the edge point through classical edge detection. And we use a simple classifier based on the direction of the gradient. We connected we labeled together, connected the edge point within the same direction class. And we remove noise and the straight arcs. We remove straight arcs through thresholding the oriented bounding box. This is a very simple approach, but still it's very effective and is pretty fast. Other methods rely on more sophisticated things such as gradient information and so on, but they're not so accurate. Then we divide the arcs in 4 classes. To do that, we need the convexity of each arc. We do this using a simple convexity detector that basically compares the areas under and above the arc. This is also an approximated method, but it works pretty good. And again, it doesn't need sophisticated information such other methods. Okay, then we apply a selection strategy. We remove the arc according to convexity, mutual position, and center location. To locate the center, we adopt a user property based on the parallel chords. Basically, the line passing through the midpoints of parallel chords in ellipses and circles passes through the center. So you can see it pretty not very good, but using 2 such lines, they intersect in the center. So if given pairs of arcs, if the 2 pairs identify the same center, they are on the same ellipse boundary. If they identify 2 different ellipse centers, they are of 2 different ellipses. So this is a pretty good selection criteria. Well, we estimated the other 3 parameters in a half transform framework. We do that using 3 1D accumulators instead of the 5D that is required by the standard half transform. This is also an optimized version of the half transform. So after we detect all the ellipses, we go through a validation process to keep only the most important ellipses, and then we cluster them together to have a single response. Well, I show you some results. Well, we can see that our method is the faster is almost as fast as the method of Libuda, but is 10% point better in accuracy. And we can also see that the other method is pretty good in accuracy, almost as ours, even if sometimes we gain 10 points. is about 100 times slower. So well, these are just some examples. Well, we show that we are able to do real-time detection with a good quality of ellipses. I present a new simple procedure to accomplish each step. These procedures are approximated, but are very efficient, and being so approximated, they don't use the information, a lot of information. And when we work with real images, this information is almost always noise. So don't use this information. It's pretty good for accuracy. And thanks to its capabilities to run in real time with low memory, it works also in on mobile devices at 20 frames per second. I published a couple of papers on this, and another one is after the first round of review with a minor revision. Now I talk to you about the recognition of places. An example is better to clarify what I want to do. I want to be able to be in front of a place, a shop or something with my cell phone. I want to recognize where I am. Usually now you do it by, if you're in front of a restaurant, you have to search on a TripAdvisor or stuff like that. You have to enter the name. It will be much easier and user-friendly to just take a picture of the logo. And obviously, we want to do this through a smartphone. So what I do is to take a picture of the shop, of whatever, and we ask the remote server to have the location. The server has some images of that place with some information related to it, such as GPS position and other kind of information, that are sent back to the user. This topic is quite similar to logo recognition, but we don't have segmented logos. We have just photos. And it's also similar to image matching, but we don't have a large data set to compare with. And the image matching algorithms are usually very computational demanding, and we want to do this on mobile phones. So these are related topics, but visual recognition is quite different. Also, to describe an image, we use some kind of descriptors. The trend of descriptors is to go to faster computation. And we find that orb is a pretty fast descriptor. It is binary. And to represent the whole image, we need a descriptor that represents the whole image, a global descriptor. Among the others, bag of words is one of the simplest to implement. So we do bag of words with the binary feature. Usually bag of words require the k-means, but on the binary space it's not defined the mean. So we use k-majority, that basically counts the number of 0 and 1s in the position of the feature, and then if the majority is 1, it says that the mean is 1, and otherwise 0. And because these features are binary, we can use Hamming distance that can be computed really fast on both PC and mobile devices. Now that I have a comprehensive summarization of the image, I can send this description to the remote server to limit the bandwidth. I can compress this description. Because the histogram is very sparse, I can achieve a really good compression rate. The compression size can be 100 times smaller, and almost half of the gzip compression. Okay. Once the data are at the server, first I can narrow the match, comparing only with the places that are in nearby. I can do this using a GPS position. I then compute the nearest neighbor using histogram intersection. That is pretty fast. I can use a ranking procedure to summarize the score of each class, and then I can return the the top matches to the final user. We developed a data set to do this. You can see there are some shops with slightly different point of view, different lighting condition, blur, and so on. Basically, we see that the approach using orb, that is a binary feature, performs better than SIFT, that is a robust, well-known feature. So the choice of binary feature is both accurate and very fast. You can see the comparison here, basically. We saw that computing the descriptor on a small image size, such as this one, it doesn't impact on the accuracy. So basically, we can compute it in on a smaller image size for a major speed up. And also, we saw that increasing the number of examples will improve the performance. So in this work, we did real-time place recognition. We are able to do this even without the GPS information. This can be a really nice feature if you want to do this in indoor locations, such as malls. Well, the app has been, in fact, developed, and it works pretty good, also for difficult images taken from different smartphones, different light conditions, and so on. I published this work 2 months ago. So to conclude, I worked in these 3 years on recognition, even if with different data goals and in different scientific areas. We reached both robust theoretical foundation or efficient and effective practical solution. So thank you very much for your attention.